So let's go back now to section 2 of the chapter, because it's actually kind of an interesting section. And I had skipped over that in order to hit a little more complicated things. But section 2 rather, is actually a little bit easier. It's how do you calculate capacitance? So we know that the capacitance is defined to be Q over V. Well, one thing that you could do is you could take, something, and you could put a voltage on it, and then you could measure the Q, and from that calculate the capacitance. But it turns out that there's another way of doing it in which you can calculate what the capacitance ought to be from the arrangement of the charges and the conductor. We're going to start with the idea of just two metal plates. One of them is positive, one of them is negative. And this is your classic capacitor. And they're going to be some distance d away from each other, and the area of each plate is going to be A. And so what happens is we're going to have an electric field between the two. Now, if the plates are fairly close together, they're conducting plates. So we know several things about this electric field. First of all, we know the electric field is a constant, and we know the magnitude of the electric field is going to be sigma over epsilon naught for a conductor. Okay, so that's the magnitude of the electric field, sigma over epsilon naught. All right, so we also happen to know that the voltage, the electric potential, is integral E dot ds. Okay, well, if the electric field is constant, it comes out of the integral, and this is going to be E times D. Okay, so capacitance is going to be Q over V. Well, Q is sigma times A, and V is going to be essentially E times D. But we also know that E is going to be also equal to sigma over epsilon naught. And so you do a little bit of algebra, and we come up with epsilon naught A over D. So that is the capacitance for a parallel plate capacitor. So you got a parallel plate capacitor, okay, all you need to know is the area and the distance here. And so there you have it. You can change the capacitance by you can pull these things apart, okay? If the capacitance is epsilon naught A over D, if you pull it apart, then what happens is the capacitance increases. You put it closer together, you pull it apart rather, then the capacitance decreases as D gets bigger. If you put them closer together, the capacitance increases as D gets smaller. If area is bigger, then once again you would have a bigger capacitance. In fact, that was a way that tuners in early radios. In early radios, you had these little discs, and the discs were set. They could open and close. Some of them could open and close. When you turn the dial, then some of these discs opened up, and they were slit little discs. So as you turned it, this little opening would increase. Okay, you turn it the other way, it close up. Okay, so it's really two discs or semi discs, sliding past each other that made that. And so what would happen is it would increase and decrease the area. If you increased and decreased the area, you would increase and decrease the capacitance, and that's how you tuned a radio. So that's an example of this. So this is how you find the for a parallel plate capacitor, then it's just epsilon naught A over D.